Image formation by lenses. A lens is an optical device that refracts most of the light falling on it. Due to its spherical shape, it refracts the light at different angles. There are two types of lenses. A lens which is thicker in the middle and thinner at the edges is called a convex lens, and the lens which is thinner in the middle and thicker at the edges is called a concave lens. A convex lens tends to collect the light that falls on it, whereas a concave lens tends to deflect the light falling on it. Let us have a relook on some basic terms related with spherical lenses. A lens is bounded by two surfaces. The radii of the two spheres, of which two surfaces of the lens form a part, are called the radii of curvatures of the lens, and the corresponding centers are called centers of curvature, and the geometric center of the lens is called the optical center of the lens. Furthermore, the line that passes through the optical center and the centers of curvature is called the principal axis. Every lens has two focal points that are located on the principal axis at the midway between the optical center and the centers of curvature. In case of a convex lens, focal point on the side of incident rays is called first focus, and the focal point on the side of emergent rays is called second focus. Whereas, in case of a concave lens, focal point on the side of incident ray is called second focus, and the focal point on the side of emergent rays is called first focus. And the distance of a focal point from the optical center is called focal length. To construct the ray diagram using a spherical lens, certain rules are to be followed. An incident ray traveling parallel to the principal axis after refraction through a convex lens passes through the second focal point. On the other hand, the incident ray traveling parallel to the principal axis after refraction through a concave lens appears to pass through the second focal point. An incident ray passing through the first focal point of a convex lens after refraction becomes parallel to the principal axis, and the incident ray directed towards the first focal point of a concave lens after refraction becomes parallel to the principal axis. An incident ray passing through the optical center of the lens refracts without any deviation. From a point of object, though an infinite number of rays travel in all possible directions, but for the determination of the position of image, we choose any two convenient rays out of the mentioned three rays. The point where the rays meet or appear to meet after refraction from the lens is the image of that point of the object. In the similar way, image of each point of the object can be obtained, and all these image points altogether form the complete image of the object. We know in general an image can be of two types, real and virtual. If the rays of light from a point of object after refraction through the lens actually meet at a point on the other side of the lens, the image point so formed is real. If a screen is placed at this point, the image will be formed on the screen. That is, a real image can be obtained on a screen. Furthermore, a real image is always inverted with respect to the object. On the other hand, if the rays of light from a point of object after refraction through the lens do not actually meet at a point but appear to diverge from a point on the same side of the lens, the image point so formed is virtual. If a screen is placed at this point, no image will be formed on the screen. That is, a virtual image cannot be obtained on a screen. Furthermore, a virtual image is always erect with respect to the object. Let us see how to draw a ray diagram to determine the position and the nature of the image formed by a lens. First, draw a line as the principal axis of the lens. Then, choose a point O on this line as the optical center of the lens. Also, draw a vertical line passing through the point O that acts as a thin lens. One can show the bending of an incident light ray from this line only to get the emergent ray after refraction through the lens. Also, choose a proper scale and mark the two focal points on the principal axis. It should be kept in mind that most commonly we use a biconvex or a biconcave lens. That is, both the focal points are equidistant from the optical center. To draw an object, its distance from the optical center and its height are to be drawn according to the chosen scale. To draw an incident ray, one can draw a line from the top of the object, and by following the rules for construction of ray diagram, one can obtain the desired image. If the two ray or lines actually intersect at a point, then the point will act as the top point of the image. But if the two lines do not intersect at a point, then one can obtain the point of intersection by drawing the two lines in backward direction. Let us see the nature and the position of images of an object at different positions. For a convex lens, as long as the object is placed at a distance more than the focal length of the lens, a real image is obtained on the other side of the lens. When an object is at a very large distance in comparison to the focal length of the lens, the object is treated to be at infinity. When an object is placed at infinity, the light rays from the object are considered parallel to each other. The ray which passes through the optical center after refraction moves without any deviation, and the ray which passes through the first focus of the lens after refraction becomes parallel to the principal axis. Therefore, a real inverted and diminished image is obtained at the second focus. This is the case when the lens is used as burning glass. and in camera when the object lies very far from the lens and the image is formed at the film, which is at the second focus of the camera lens. When the object is placed beyond 2f1, the ray which passes through the optical center after refraction moves without any deviation, and the ray which is parallel to the principal axis after refraction passes through the second focus. And a real inverted and diminished image is obtained between f2 and 2f2, as can be seen. This is the case of a camera lens when the object is not very far away from the lens. When the object is placed exactly at 2f1, a real inverted image of the same size as that of the object is formed at 2f2. This type of image formation is used in terrestrial telescope. And if the object is placed between 2f1 and f1, again a real and inverted image is formed, but beyond 2f2. Here, it can be noticed that the image is magnified. Such type of image formation is used in projectors. Here, magnified image is obtained on the screen placed on the other side of the lens of the projector. But when the object is placed exactly at the focal point, an image is formed at infinity, because the refracted rays are parallel to each other and they can never intersect each other. Such type of image formation is used in collimators, where a parallel beam of light is required. And if the object is placed at a distance less than the focal length of the convex lens, both the emergent rays never intersect each other. But when produced backward, they meet at a point in such a way that a virtual, erect or upright, and a highly enlarged image is formed on the side of the object. This type of image formation is used while using a convex lens as a magnifying glass or a simple microscope or as a reading lens. For a concave lens, when an object is at a very large distance in comparison to the focal length of the lens, that is, the object is at infinity, the incident light rays from the object are considered parallel to each other. The ray which passes through the optical center after refraction moves without any deviation, and the ray which moves towards the first focus of the lens after refraction becomes parallel to the principal axis. In this situation, two rays never intersect each other, but when produced backward, they meet at a point which is on the focal plane passing through the second focus of the lens. Therefore, a virtual, erect and highly diminished image is obtained at the second focus, that is, on the side of the object. This type of image formation is used in Galilean telescope. Unlike a convex lens, when the object is placed in front of a concave lens at any place, a virtual, erect and reduced image is formed on the same side of the lens. This type of image formation is used in spectacles for a short-sighted person. It can be noticed that when the object is placed exactly at the focus of a concave lens, image is obtained exactly at the midpoint between the optical center and the second focus of the lens. In general, irrespective of the position of the object, the image formed by a thin concave lens is always virtual, erect, diminished, and situated on the side of the object between the optical center and the second focus of the lens. However, in case of a thin convex lens, both real and virtual image can be obtained depending upon the position of the object. The size of the image also depends on the position of the object. A real, inverted and diminished image is obtained when the object is placed at a distance more than twice of its focal length. And the size of the image becomes same as that of the object when it is placed exactly at a distance of twice of the focal length. Further, the size of the image gradually increases as the distance of the object from the lens decreases, and a real, inverted and magnified image can be obtained. But the image is formed beyond 2f. There is a situation when the image is formed at infinity. A virtual, erect and highly magnified image can be obtained by a convex lens if the object is placed at a distance less than the focal length of the lens, and it will be situated on the side of the object. Lens formula and magnification. All of us are well familiar with the converging and diverging actions of the lenses. Knowingly and unknowingly, these lenses have become a compulsory part of our life. Lenses of appropriate focal length are used in different optical devices. It is important to know the focal length and the magnification of a lens so that a lens of the desired focal length and the magnification can be used in an optical device. While dealing with refraction at spherical lenses, we have to follow a system of signs called the new Cartesian sign conventions. According to this system of sign conventions, all distances are to be measured from the optical center of the lens. The object is always placed to the left of the lens so that the incident rays always travel from the left to the right direction. All distances to the left of the lens are to be considered as negative. All distances to the right side of the lens are to be considered as positive. All heights above the principal axis are to be taken as positive, while the heights below the principal axis are to be taken as negative. As a result of these sign conventions, the object distance is always negative because the object is placed to the left side of the lens. The distance for a real image is positive as the real image for a spherical lens is formed at the right side of the lens. For a virtual image, the image distance is negative as it is formed at the left side of the lens. The height of the object is always positive as the object is placed above the principal axis. The height of a real image is negative as the real image is always inverted and formed below the principal axis. The height of a virtual image is positive as the virtual image is always erect and formed above the principal axis. The focal length of a convex lens is always positive as its focus is marked on the side of emergent rays, that is, on the right side of the lens. The focal length of a concave lens is always negative as its focus is marked on the incident ray side, that is, on the left side of the lens. In a spherical lens, there is a relationship between the object distance, image distance, and the focal length of the lens. To obtain this relation, let us consider an object AB lying on the principal axis of a convex lens at a distance more than the focal length of the lens so that a real and inverted image can be obtained. Since an incident ray travelling parallel to the principal axis after refraction through a convex lens passes through the second focal point. Therefore, a ray of light parallel to the principal axis incident normally on the surface of the lens at point D is refracted along DF. Furthermore, an incident ray passing through the optical center of the lens refracts without any deviation. Therefore, an incident ray of light passing through the optical center of the lens is refracted in the same direction, that is, along AO. The two emergent rays intersect each other at a point, say, A'. Hence, A', B' is the required real and inverted image. Here, OB is the object distance and OB' is the image distance. In the triangles ABO and A'-B'-O, right angle ABO is equal to the angle A'-B'-O. Angle AOB is also equal to the angle A'-OB' as both are vertically opposite angles. Therefore, triangles ABO and A'-B'-O are similar triangles. Hence, ratio of BA and B'-A' is equal to the ratio of OB and OB'. Since BA is equal to OD, therefore, ratio of BA and B'-A' becomes the ratio of OD and B'-A', which is equal to the ratio of OB and OB'. Also, the triangle DOF and A'-B'-F are similar triangles. Hence, ratio of OD and B'-A' is equal to the ratio of FO and FB'. From the two obtained ratios, ratio of OB and OB' comes out to be the same as the ratio of FO and FB'. Since OB is the distance of the object, OB' is the distance of the image, FO is the focal length of the lens, and FB' is the difference between the image distance and the focal length. On substituting the corresponding values using sign conventions, one can obtain a relation between the object distance, the image distance, and the focal length of the lens as shown. This is called lens formula. This formula is valid for a thin convex as well as a thin concave lens. This is also valid for any position of the object or the image. Let's see an activity. Here we have a convex lens, an arrow-shaped slit that can be used as an object, and a white screen that can be used as an image when a clear image is obtained on the screen. Initially, the slit is 15 centimeters away from the lens. Since the object distance is always negative, thereby the object distance u is minus 15 centimeters. By adjusting the screen, we obtain sharp inverted and enlarged image on the screen, and the distance of the screen from the lens can be used as the image distance, which is 30 centimeters. With the help of lens formula, one can measure the focal length of the lens, which comes out to be 10 centimeters. Let us now fix the slit, that is the object at a distance of 20 centimeters from the lens. On adjusting the screen, a sharp image is obtained at a distance of 20 centimeters on the other side of the lens. This again shows the focal length of the lens is 10 centimeters. Further, if we fix the object at a distance of 25 centimeters from the lens, a sharp image is obtained at a distance of 16.67 centimeters from the lens. This again shows the focal length of the lens is 10 centimeters. Let's try some problems. Find out the focal length of a convex lens if an object placed at 20 centimeters from it forms a real image at 30 centimeters. Here, object distance u is minus 20 centimeters and image distance v is 30 centimeters. By using the lens formula, focal length can be obtained as 12 centimeters. Let's look at another problem. A concave lens has focal length of 15 centimeters. At what distance should the object from the lens be placed so that it forms an image at 10 centimeters from the lens? Since focal length of a concave lens is always negative, thereby it is minus 15 centimeters. Furthermore, a concave lens always forms a virtual erect image on the same side of the object. Therefore, the image distance is minus 10 centimeters. By using the lens formula, the object distance comes out to be minus 30 centimeters. That is, the object should be placed at a distance of 30 centimeters away from the lens. An object 5 centimeter in length is held 15 centimeter away from the converging lens of a focal length 20 centimeters. Find the image distance. Since a convex lens is a converging lens, thereby its focal length is always positive, which is given as 20 centimeters. Here the object distance is minus 15 centimeters. By using the lens formula, the image distance comes out to be minus 60 centimeters. Here, negative sign shows that a virtual image is formed at a distance of 60 centimeters away from the lens. There is one more important term generally used to define a spherical lens. That is, linear magnification of the lens. It is the ratio of the size of the image formed by the lens to the size of the object. It is represented by m. According to the system of new sign conventions, the size of the object, that is, h1, is positive as it is always placed above the principal axis. Size of the image, that is, h2, is negative for real image as it is an inverted image and thereby the linear magnification for a real image is negative. Size of the image, that is, h2 is positive for a virtual image as it is an erect image and thereby the linear magnification for a virtual image is positive. Since the ratio of the size of the image formed by the lens to the size of the object, that is, ratio of B'(A' and BA is equal to the ratio of OB' and OB. Therefore, by substituting the corresponding values and using the proper sign conventions, linear magnification can also be expressed as the ratio of the image distance to the object distance from the optical center of the lens. The distance of the object from the optical center, that is, U, is always negative as it is always placed on the left side of the lens. Distance of the image, that is V, is always positive for real image as it is on the right side of the lens, and thereby the linear magnification for a real image is again negative. Distance of the image, that is V, is negative for virtual image as it is also on the left side of the lens, and thereby the linear magnification for a virtual image is again positive. It can be concluded that m is greater than 1 when the image is enlarged and less than 1 when the image is diminished. Also, negative value of m indicates that the image is real and inverted, and a positive value indicates that the image is virtual and erect. Let's see a numerical problem. A 2.5 centimeters tall object kept in front of a concave lens at a distance of 15 centimeters produces a 2 centimeters tall virtual image. Calculate the magnification and the focal length of the lens. Since a virtual image is always erect, therefore, object height and the image height both are positive. Here, h1 is given as 2.5 centimeters and h2 is given as 2 centimeters. Hence, the magnification m comes out to be 0.8. This ratio is also equal to the ratio of the image distance and the object distance. Knowing the value of the object distance, image distance comes out to be minus 12 centimeters. Now, using the lens formula, focal length can be obtained as 60 centimeters. Here negative sign shows that it is a concave lens. An object 5 centimeters in length is held 15 centimeters away from a converging lens of focal length 20 centimeters. Find the image height. By using the lens formula, the image distance comes out to be minus 60 centimeters. And the magnification of the lens comes out to be 4. Further, the linear magnification is also the ratio of image height and the object height. Therefore, the image height comes out to be 20 centimeters.